In the last lectures, we have computed some basic examples of Laplace transforms for some easy to compute functions. Now, to compute more Laplace transform of more functions, we will need to establish some theoretical properties of the Laplace transform which will help us in the computations. So, in this lecture we will do this, and today we will see some properties like linearity property of the Laplace transform, change of scale property, and the first and second shifting properties. Let us begin with the linearity property of the Laplace transform. It says that if we have two functions, if f and g are two functions with Laplace transforms fs and gs, so our functions are again variables in t, and the Laplace transforms are variables in have variables s. Now, given two functions f and g with the given Laplace transforms capital Fs and capital Gs, suppose we take constants. Suppose that alpha 1 and alpha 2 both are positive constants, then the Laplace transform of the function alpha 1 f plus alpha 2 g, and this is given by, so this is a variable in s, this is given by alpha 1 Laplace transform of f with variable s plus alpha 2 Laplace transform of g with variable s, and this is nothing but alpha 1 fs plus alpha 2 gs. This is the linearity property of the Laplace transform, and it says that when you multiply your functions with constants, those constants can be taken out of the Laplace transform, and when you add two functions, the Laplace transform of the added function is the sum of the Laplace transforms of the individual functions. So, here we should mention what is the region of convergence for this function, for the Laplace transform of this function. So, what is the region of convergence of alpha 1 fs plus alpha 2 gs? Region of convergence. So, remember that whenever we compute a Laplace transform, we have to specify the region of convergence as well, otherwise the answer is deemed incomplete. So, let us try to understand what is the region of convergence of this function alpha 1 fs plus alpha 2 gs. So, suppose that fs has region of convergence s greater than c1 for some constant c1 greater than 0, and similarly suppose that gs has the region of convergence given by s greater than c2 for some c2 greater than 0, then the region of convergence for alpha 1 fs plus alpha 2 gs is given by the region s greater than maximum of c1 and c2. So, we have the real line, this is the s line, and suppose that this is c1, so fs is defined in this region the red arrow describes, and on the other hand suppose that we have c2 and the region of the blue arrow describes the region of convergence of GS, then the maximum of C1 and C2, so in this case this is C2, this will be the region of convergence of alpha 1 Fs plus alpha 2 Gs. So in general, whenever you have two regions of convergence for functions f and g, you can take the intersection of these two and you will get the region of convergence for the sum. So let us try to compute an example using this property. So let's suppose that ft is equal to the hyperbolic cos function cos ht. So remember that the hyperbolic cos function, cos h function, is given by e to the power t plus e to the power minus t over 2 for t greater than or equal to 0. So our Laplace transform of this function ft will be the Laplace transform of half e to the power t plus half e to the power minus t, but by the linearity property this is given by half Laplace transform of e to the power t plus half Laplace transform of e to the power minus t. And we know the Laplace transform of e to the power alpha t for any constant alpha. We have computed it before, and this is half 1 over s minus 1 plus half 1 over s plus 1. And here the region of convergence will be s greater than maximum of 1 and minus 1, because this is defined for s greater than minus 1 and this is defined for s greater than 1. So the sum is defined in the region s greater than 1, the maximum of 1 and minus 1, which is 1. So let's try to compute this expression. So we have half 1 over s minus 1 plus 1 over s plus 1, and this is given by half s plus 1 plus s minus 1 over s minus 1 times s plus 1, which is s by s squared minus 1, and we have seen that this is valid for s greater than 1. So this is the Laplace transform of the function hyperbolic cosine t. So we see that this linearity property helps us compute the Laplace transform of more functions. So let's try to give a proof, which is a very easy proof for this linearity property. So we try to compute the Laplace transform of f t plus alpha 2 gt, alpha 1 f t plus alpha 2 gt, and this is by definition. Again we use the definition of the improper Riemann integral from 0 to r alpha 1 f t plus alpha 2 gt dt. So this is given by the limit r goes to infinity. Now I can use the linearity property of the integral of the Riemann integral to get the following expression. You have alpha 1 integral 0 to, so I missed here a factor of e to the power minus st, sorry. So you get ft e to the minus st 0 to r dt plus alpha 2 0 to r gt e to the minus st dt. And now you can take the limit inside and you get easily the Laplace transform of ft plus alpha 2 Laplace transform of gt, which is given by alpha 1 fs plus alpha 2 gs, and this is for s greater than maximum of C1 and C2, where we assume that capital Fs is defined for s greater than C1 and capital Gs is defined for s greater than C2. So this is a very easy proof. Now let's look at the second property, which is change of scale. This says that suppose that the Laplace transform of a function ft is given by some function capital Fs for s greater than alpha, and so now suppose that lambda is a positive constant, then the Laplace transform of the function given by f of lambda t, so this is changing the scale of the domain of f by a factor of lambda, which is why it's called change of scale. So now this is given by 1 over lambda f of s over lambda, and the region of convergence for this function is given by alpha lambda. So let's see a proof of this property. So we can start with the Laplace transform of f of lambda t. This is by definition 0 to infinity f of lambda t exponential minus st dt. One can use improper Riemann integrals and write the limits, etc., but since now it is clear what it should be, I am just writing 0 to infinity for shorthand notation. Now I can make a change of variables given by u equals lambda times t. So this implies that du is lambda dt, and let's look at the limits of integration. So if t equal to 0, this implies that u equal to 0 because it's just lambda times t, and when t equal to infinity, u is also equal to infinity because we have assumed lambda to be a positive constant, since lambda is a positive constant. So then our integral becomes f of lambda t st dt. This becomes 0 to infinity f of u exponential minus s. Now t is given by u by lambda and dt is given by du over lambda. So now we can take the factor of lambda out of the integral. So it's 1 over lambda 0 to infinity fu exponential minus s over lambda times u. So I will just rewrite it in this form, du, and now it becomes clear that this is the Laplace transform f of the function, original function ft, evaluated at the point s over lambda, because you have this coefficient as s over lambda. The other parts of the integral remain the same. So this is just the Laplace transform of f evaluated at the point s over lambda. Now the only thing left is to see that is the region of convergence for this function capital F s over lambda. Note that original function fs was defined in the region s greater than alpha. So since we are changing the scale here, we should need s by lambda greater than alpha, so that this capital F is well defined, and this is equivalent to saying that s is greater than alpha lambda. So we have shown the change of scale property.